Yes, I know, but I did.
James, you have your phone?
No.
No, they don't have it today.
Oh, yeah, I'm sorry. I can put in 7 minutes. Oh, you can.
I'd like for us to finish up the rest of the packet before we move into the test review. So we can start with 31. This is also review as well. So let's finish this first, and then well, at least up to page 33. And then we can look at yeah, the rest of your test review. So start with 31. These are all either one-sided limit or limit as x approaches infinity or infinity. If it's approaching infinity, that means you're just following the graph to the left or to the right as it extends past what we see. And you can kind of imagine that these are arrows extending past what's in view. And then if we're approaching 1 or -1 from the left or from the right, then these are one-sided limits. A lot of them are approaching asymptotes. They can indicate that. Okay, so try these first, and then we'll compare our answers in a bit. Should be fast.
Good morning. Pardon the interruption. There is map testing today. Students who are testing received a pass on Friday or this morning. Please have them report to the media center. Thank you.
Okay, so as we approach positive infinity, this arrow to the right is indicating what's happening. We can see that this actually does approach a horizontal asymptote. So the limit as x approaches infinity is going to be 2. As we approach negative infinity, we're going to follow the left arrow as it exits our graph, and that's going to head towards a y value of 0. As we approach from the left, Frankie, you can also pick up can't get there. Approaching 1 from the left, we can see it's approaching our y values. X value is approaching a vertical asymptote, sorry, and our y value is approaching positive infinity. From the other side of the vertical asymptote, also headed towards positive infinity, approaching 3 from the left, another vertical asymptote, positive infinity, approaching 3 from the right, also vertical asymptote, so positive infinity. And if we're approaching the same number from the left and from the right, and they're both giving you infinities, you know there's a vertical asymptote there. Even if this wasn't drawn for you and this property was given to you, you would know that this is talking about vertical asymptotes. And then for 15 and 16, we're just identifying what we see in front of us. '17 through 23.
For 17 to 23, is that what graph is that based?
I think it's the same. Oh. Approaching 0. Oh, sorry. I don't think I provided that graph. I thought I had that. Sorry, so skip that. My bad. Okay, page 32. So I want to clarify a few things, and I just wanted to highlight again, the biggest issue that students have with limits is trying to nail down that first step. And I think our tendency, at least from what I've seen, students want to skip to the second step. And if you skip to the second step without doing the first step, then you're making certain assumptions, and if that assumption is not correct, then you're going down the wrong path. So your first step is always one of two things. Okay. If its limits approaching a real number, it doesn't matter if it is one-sided limit, we're always going to do direct substitution. Right, so if I have limit as x approaches 3 from the left, and I have x plus 2 over x minus 4, I'm always going to just plug in the integer value, not the decimal, right? So this will be 5 over -1, right? So that should be your first step, right? Then after whatever you get after that, then you can make your decision and you can make your, you can decide what to do next, okay? And then if limit as x approaches c of f of x, where c is plus or minus infinity, then we always compare degrees. So limit as x approaches infinity of, let's say, you compare degrees higher in the numerator than denominator, then we know that there's no horizontal asymptote. Degree in numerator is higher than denominator. This is getting larger and larger up top than below. Then you know it's either plus or minus infinity. Now you can decide that you want to test a number that is in the direction that we're headed, right? So but this is what I see students do, okay? And so these are not first steps, even though it may be tempting. And then you can imagine like this one, right? Students want to do decimals. And they want to do 2.9 plus 2 over 2.9 minus 4. And then they're just trying to get to some decimal value, and that is not correct, right? So we don't want to do decimals is never your first step, okay? And then the other issue that students experience is they want to plug in a number in the direction that they're headed, and so they start to test 100. But remember, degrees is the first step, not plugging in a value. And so here students would get stuck not knowing what this means. And they don't know what to do with this. And they say, well, this is just some positive number. And then they would say positive infinity. But that's not correct, right? Degrees come first. You know the limit is going to be 1. It's not positive infinity because degrees are the same. And so I see a lot of students run into these issues where they do a decimal or they plug in 100 and they haven't gone through the first steps yet. Right? So that's the biggest issue that students experience on the test. So if you can nail down the first step, you're going to have a better knowledge as to, then you can decide what your next step is, right? But if you don't have the first step, if you jump the gun, then you're taking a risk, and a lot of times, you're kind of already invested into this step, and so it's hard to backtrack. It's hard to backtrack and realize that you've gone down the wrong path if you don't do the first step. Okay. All right, so that's the biggest thing. All right, so let's go to page 32. Wait, did we try some? No, we haven't. Okay, so 27, go ahead and try that. So no decimals and no plug in 100 or infinity, right? Those are not the first steps. All right, so try 27, and then I'll follow up the steps as you guys try each problem. Okay. Direct substitution tells us 6 over 0. So we know there's a vertical asymptote at x equals 2. We know visually what's going on. We know the true limit doesn't exist. But we realize, oh, wait, this is not asking for the full limit. Now we can look back and realize, okay, this is a good situation where we can involve decimals. Okay, now we involve decimals because we realize after direct substitution that there's a vertical asymptote, and they're just asking about what the approach towards that asymptote looks like. (1.9) into the and for x, again, no need for calculator, and also there will be this will be a non-calculator test. Numerator gives me positive, denominator gives me negative. That's enough for me to know, okay, as we approach the asymptote, my arrow is headed down, going down towards negative. Right, try 29. Again, direct substitution tells us there's a vertical asymptote. We know the limit doesn't exist. And now we know that this is the appropriate time to involve decimals when there is a vertical asymptote and a one-sided limit. (31) again, direct substitution gives us indication that there's a vertical asymptote. Then now it's the time to involve decimals. When we're approaching a negative number, just recognize that things are a little bit opposite. So in this case, on number line, if this is -1, then a number slightly to the right of -1 will be -0.9. So 5 times a number slightly less than 1 would be around like 4 something or -4 something, 4.8, 4 point something. Still going to be a negative number. And then negative times positive is negative, so therefore positive. Okay, 33. Direct substitution tells us there's a vertical asymptote approaching one-sided limit towards that vertical asymptote. We can then play with decimals. But then we realized that if we were to plug through direct substitution, and if we're getting a 0 over 0 or a real number, then the one-side limit has no impact, right? You're just going to treat it like a normal limit problem. The limit will exist. One-side limit is not going to play a role at all. It's only going to play a role with decimals if there's a vertical asymptote and you're approaching that vertical asymptote. 35. So 35, it's not asking for a one-sided limit. You could stop and say that the limit doesn't exist because it's not asking from the left or from the right. But just wanted to highlight that we could also gather more information by doing one-sided limit, because we know that there's a vertical asymptote, and seeing if there's an agreement. If you have agreement on a full limit where a limit doesn't exist, then there's a subcategory that you can say is negative infinity. So I want to show you here. Let's say I have this situation. Here, if you say limit doesn't exist, that is true because it's approaching that vertical asymptote. But if you're asking for more specific as to why it doesn't exist, if the two arrows are in agreement, we can do a subcategory and say it doesn't exist because both have an agreement at positive infinity. So if you see limit is equal to positive infinity and it's not a one-sided limit, that means this is what the graph looks like. That true, it doesn't exist, but that just means that there's both graphs share the same behavior. Likewise, if the graph looks like this. You see negative infinity, that means there's agreement in terms of their behavior. But then if the arrows are not pointing in the same direction, then there's no subcategory. We just leave it as B and D. So these are all doesn't exist. But if the arrows are pointing the same direction, we can give a little bit more detail as to why it doesn't exist. Yeah.
So then would you write your final answer as like B and E, but then parentheses plus under?
It depends. Depends on what the instruction is telling you. If the instruction says, give me more information than B and E, then if possible, then you want to provide this information for those. But if the graph looks like this, then there's no subcategory, just D and E. All right, 43. Positive infinity. We don't do that. We don't plug in 100, right? We're not ready for that. We compare degrees. Degrees is higher in the denominator. What conclusion can we say about the limit here? Equals 0. Yeah, there is a horizontal asymptote. My denominator has a higher degree. This fraction is getting smaller and smaller and smaller. Start plugging in 100, then you're making an assumption that the limit doesn't exist, but the limit does exist here. Okay, hopefully these will go fast. Page 33, 47 to 60. These 4 problems here. Again, infinity, you got to compare degrees, right? You don't want to plug in 100 or negative 100 unless your comparison of degrees tells you that it is appropriate to test 100 or negative 100. again, you're only plugging in either 100 or negative 100 if you realize after comparing your degrees that your numerator has higher than your denominator. That's the only time that you're going to have to decide between plus or minus infinity, and then you can test either 100 or negative 100, depending on which direction the graph is headed. Okay, any questions? All right, now let's move into our test review packet. So for number 1 and 2, I think I'll make a slight adjustment. I'm going to say this is 0 approaching from the left. So 0 is the negative, and this is -3 from the right. But we talked about how one side limit shouldn't throw us off, right? We're still going to stay disciplined, and we're still going to take our first step. Okay. So what's the first thing we do for number 1? Yeah, direct substitution. Okay, try that. Okay, what does that tell us? What information do we get after direct substitution? 0 over 0. What does that tell us? There's a hole. Does the limit exist? Yes. Does the one-side limit play a role for us? No, doesn't play a role, right? We don't plug in decimals unless there's a vertical asymptote, right? So I know how tempting it is, because you look at that 0 negative and you want to say, oh, I want to do decimals. I want to do negative 0.1 or I want to do 0.1, but you're only doing that if there's a vertical asymptote, right? If it's a 10 over 0, 8 over 0, then the one-side limit can play a role, right? But here, that's just a distraction. Just a distraction. This is a full limit here. This is like as if we're getting a full limit. You're going to get, this will be the same as approaching 0, as approaching 0 from the right. So ignore the one-sided limit. Okay, there's a specific strategy for this, right? If we see radicals here, we know it's hard to cancel out. We know it's not factoring. We're going to go through our conjugate method, right? So I need to multiply the top and bottom by the conjugate of the numerator. Expand out your numerator. And remember, the whole point here is you're trying to get the numerator to show you an x because you know that this x is already causing the 0, but you know there's an x hiding in the numerator that's also causing a 0. And you're hoping that an x will show up in the numerator so they can remove the two x's above and below and then reevaluate. And then it should remove the whole and get you down to a real number. FOIL out. Multiply the first pair together. Multiply the second pair together. The middle pairs will just drop out, so you don't have to worry about them. And then don't expand your denominator. The x is ready for you to pair up and cancel out. So don't distribute the x through. Okay. What's left in the numerator? Just x, right? The 19 minus 19 goes away. That's perfect. That's exactly what we want. We want there to be a matching pair for us to remove. And then once we remove the x, then we can do our final limit evaluation. What's left in the numerator after everything cancels out? Just 1. Okay, what do we do from here? 0, right? We don't do decimals, right? We talked about already that there is no place for decimals here. It's just there to throw you off, right? So plug in 0. We get root 19 plus root 19. Add like terms, we get 1/2 root 19. If you leave it like this, that's fine. If you feel like you just want to rationalize the denominator, that's fine as well. But you won't get points taken off because you left your answer with a radical in the denominator. So this is perfectly acceptable. All right, try number 2. Approaching -3 from the right. -3 with a plus here. What's our first step? Like a -3. What do you get? 0, 0. What does that tell you? So there's a hole. The limit exists. Do we play with decimals? No. Just ignore it. It's just limit as x approaches -3. That's it. Right? You should be able to find a common factor, numerator and denominator, cancel that out, reevaluate, and you should be able to arrive at a real number. All right, any questions with 2? By the way, if you're working ahead of me, that's fine. Just know that the key is attached so we can check your progress and move ahead if you're ahead of me. Feel welcome to jump ahead if you're already comfortable with the problem that I'm going through. All right, let's look at number 3 here. Number 3 feels a little bit more intimidating with that absolute value, but we know that we can always break an absolute value function into a linear function. So I'm just going to step to the side and just think about, what does that absolute value of x minus 2 look like? What does it mean? So absolute value of x minus 2, you know that this is a graph that looks like this. There's a vertical asymptote, there's a vertex at 2, and the graph is going to kind of have a V shape. And if you think about a V-shaped graph, this is just a combination of 2 linear graphs, right? I have a linear graph with a positive slope. I have a linear graph with a negative slope. They just happen to start and end at the same point. The end of one graph is the beginning of the other, and they meet at 2, 0. So with absolute value of x minus 2, I know I can break it down into 2 linear graphs. One linear graph is just the x minus 2, and that graph is only living to the right of 2. That's talking about this branch to the right. So this piece is that. Meanwhile, we also have a negative slope version of the linear graph, and that is negative parentheses x minus 2. That will show the negative slope version, and that is to the left of 2. Are we good with breaking down that absolute value into its linear components? Okay. Now, that's not what we really want, right? What we really want is divided by x minus 2. There's only a portion of it. So if I divide by x minus 2, that means I got to force next divide by x minus 2 to both of my linear components. And let's see what that cleans up to be. X minus 2 over x minus 2 just becomes what? 1 to the right of 2. And this becomes what? Negative 1. And that is to the left of 2. And now, if you have this to read, it's a lot easier to interpret, right? If we're approaching 2 from the left side of 2, which piecewise will be more appropriate? Top or the bottom? Bottom, because approaching 2 from the left means 1.9, 1.99, 1.999. That's all over here. And that approach is headed towards what? Negative 1. That's our answer, negative 1. Does that make sense? Any questions? That. Okay, number 4. Again, let me put a 0 from the left for that as well. 0 from the left. What's our first step? Zero substitution. Again, there's a hole. The limit exists. Ignore the one-side limit. No decimals here. Right? No decimals. Now, this is a special case here. We know that there is a hole that's hiding in the numerator and denominator. We know we got to cancel that out, but it's not a factoring problem. It's not a conjugate problem. This is going to be involving, this is a complex fraction involving common denominators. So what we want to do is we want to focus on trying to get this portion to be cleaned up. We would like to merge that into one fraction. And then if I can get that down to one fraction, then it's a lot easier to know, to work in that x and hopefully cancel things out and reevaluate. So we need to work on building common denominators first. So I'm just stepping to the side here and finding common denominators so that I can merge these together. My common denominator is just going to be x plus 1. No change between my old denominator and my new denominator, so I'm just going to carry that 1 down. Second fraction, there is a change. This to this, I need to multiply by x plus 1. Let's merge them into the same fraction. I get 1 minus x minus 1 all over x plus 1, which is negative x over x plus 1. So this is now the updated version of this 1 over x plus 1 minus 1. This is going to be the more helpful version for us. Let's rewrite the limit. Negative x over x plus 1 all over x. Dividing by a value is same thing as multiplying by its reciprocal, especially if we're dealing with a complex fraction. So dividing by x is same thing as multiplying by its reciprocal times 1 over x. And this is what we want. We know there's a hole that's causing that 0 over 0. And now we can clearly see how we can remove those holes. And that should allow us to get a better read on our limit. There's a negative 1 that's above. There's an x plus 1 below. Plug 0 in for x. We get negative 1 over 0 plus 1. So negative 1 over 1 is negative 1. Okay, any questions with 4? All right, number 5. What's different about number 5? Compared to previous problems. And what do we do with infinity? Compare degrees. Yeah. No, we don't plug in 100, right? We don't do that unless something tells us to do that. Okay, what's the degree of my numerator? What's the degree of my denominator? Also 5, right? They may be out of order, so you have to go through and look at each degree and find the highest one above and below. What do we notice? Degrees are the same, so it's just the ratio of the coefficients. 4 over 2, 2. All right, first step is so important. If you can get the first step down, then everything else should fall into place a lot easier. Six is a little bit strange here because it's infinity, but it's hard to compare degrees in that form. So is there a different way that we can maybe rewrite this problem? Yeah, x to the 5th over 3 to the x. Even then, this is doesn't seem like we can compare degrees because it's not a rational function. This one is a comparative growth rate problem. Okay, we have different families of functions above and below. What category is the numerator? Polynomial. Denominator is a exponential. So we got to compare which grows faster, and then we know it's either plus minus infinity or it's going to be 0, right? It's going to be one of those two. Which side is growing faster? Denominator. Therefore, my limit is 0. My fraction is getting smaller and smaller, and eventually it's going to approach 0. Okay, Number 7. Back to real numbers. First step. Direct substitution. So we're just plugging in what? -3, just -3, right? Okay, numerator, we get what? 12. Yeah, just keep in mind the -3 squared. The squared is impacting the negative there, so it's 9 plus 3 is 12. Denominator, we get 0. What does this tell us? Vertical asymptote. Does the full limit exist? The full limit is D and E, but is it asking for the full limit? No. Now you can do what? Now it's decimals. Okay, so you got to get through all this before you can involve decimals. Right? Careful, we're on the negative side here. So what's to the left of -3? -3.1. Yeah. And you're just using your numerator and denominator to decide between two options. It's either going to be plus infinity or it's going to be negative infinity. Okay, try number 8. Okay, what's our first step? Direct substitution. What do we get? Yep, non-zero over 0. There's a vertical asymptote, but it's approaching 1 from the right. Now you can plug in a decimal value because you're trying to figure out how is the graph moving, right? You know it's one of two things, either doing this or it's going to go down. So after there's a confirmation that there's a vertical asymptote, then you can commit to a decimal value. You can plug in the 1.1. Okay, your homework, pages 1 through 4. And if you're getting stuck on any problems as you work through your homework, don't worry about it. We're going to go through every question you have tomorrow. So your test is going to look most like page 1 through 4. Okay, I included some additional pages for you to practice, but this is page 1 through 4 is your best representation of what your test will look like on Friday. Yeah. No, don't worry about the other. The rest of the pages from your original packet, I can go over them during help sessions, but I'm not going to assign them for homework. So first, your homework, page 1 through 4, and second, your test is Friday. I'm going to have 2 help sessions here. So help session, and I'll include this in my text remind that I send out. It's going to be Wednesday from 7:30. And then Thursday as well. But Thursday will be abbreviated because I have a meeting. So 7:15 to 7:40. But I'll send all this information reminder this afternoon to remind. Okay, that's all. Bell's gonna ring at 9:17 in a minute, and then after the bell rings, you guys can get your phones. Have a great day, guys.
Oh, weird. Enjoy, trust my food. Okay, next. Yeah. This name's Munson. Here yet. It's fine. Oh, there you go. I'll do that right now.
Come ready, hey guys, see you tomorrow.
Yeah, my slide was like there.
Bye, thank you. Thank you.
Oh, I'm approaching. That would be on.